You're welcome to Sa Majesty Easy World Science Channel, the Easy World of Science. Today, we're going to be handling Boyle's Law. So, Boyle's Law will be treated in details, and the outcome of the class will include the wordings of the law and the mathematical equations, wordings of the law, then the explanation using diagram where necessary. So you see here the explanation, the graphical representation, the calculations, and the cheats, and then how to know when to use Boyle's law and when not to use it. So then the limitations of Boyle's law. So first we're going to start with the wordings of the law, which is Boyle's law. So we move to our notes here. The wordings, meaning how do we state Boyle's law? The Boyle's law states that the volume V of a given mass of a gas is inversely proportional. Boyle's law states that the volume V of a given mass of a gas is inversely proportional to its pressure at constant temperature. So, as far as Boyle's law is concerned, what is constant is temperature, and what varies is volume and pressure, and that's the one you saw there written in blue. Then mathematically, this implies also that what this means is that V is inversely proportional to 1 over P, whereby P is the pressure and V is the volume. Therefore, in inverse proportion, we have to introduce sign of constants to remove this proportionality sign. So for us to remove the proportionality sign, we have that, and remember that if P varies inversely as V, it also means that V varies inversely as V. So any of these two laws are actually correct. Any of these statements is still talking about Boyle's law. Now, to remove the sign of proportionality, we have that P or V equal to K over V. Then when you cross multiply, remember this should be P over 1. So if you cross multiply, you have that K times 1 is K equal to PV. So K equal to PV is the major topic sentence for this particular Boyle's law. It means that anytime you multiply the product of pressure and volume, that it remains a constant as far as the temperature is constant and the mass is constant. So in that aspect, Boyle's law is trying to tell us that if you bring out these two parameters, whereby anytime P is increasing, it is obvious that V will be decreasing, and that is the inverse proportion. And if PV is always a constant, this also implies that P1 V1 is equal to P2 V2, and this is the law we will be using in the calculation highlighted here. Yeah, P1 V1 is equal to P2 V2, and P2 V2 is also equal to P3 V3. So this is the wordings of the law according to our lesson plan. We have to see now after the mathematical representation, we have to see the diagrammatic representation of this Boyle's law. So here I will have to use a diagram to represent the law, in the sense that you might use a blank sheet like this. So using black here, we have that this is a square. I'll now cut it on the diagonal. I'm going to shade differently. So let me use a red. Yeah, so in this aspect here, I'm shading it red to represent either volume or pressure. Then here I'll shade it yellow. Okay, then we go to the writings. So in this case, if here is my pressure, where here is P1, over here in yellow will be V1, and I move the region shaded red. If I move up, the area decreases, but as I'm moving up, the area shaded yellow increases, and that is inverse proportion. And when you compare, P1 is greater than P2, but unfortunately it's giving us that P1 is less. Yes, of course, P1 is greater than P2, whereas V2 is greater than V1 on the inverse proportion. So the same thing, P3, and you have it V3, you have P4, V4, P5, V5. So as the size, remember that what this implies here is that from here to here is constant. That is the product of the two, such that the length covered by P1 and V1 is equal to the length covered by P2 and V2, which is also equal to the length covered by P3 and V3. So we have not exceeded this, and that is why the law is correct, which means the individual values or figures for pressure and volume might change, but in total the product of pressure and volume remains the same if the temperature remains constant. So if you watch well, that we have to represent this now by having another number, using a number that we know. Okay, let's assume that our P1 here becomes 16, our V1 is 1. Then when our P2 decreases to 8, this one will automatically be 2. Then you move again. If this is 4, this will also be 4. Then when this one decreases by 2, this becomes 8. Such that when pressure becomes 1, volume will increase to 16. So you see the inverse proportion. You are moving from 16, 8, 4, 2, and 1. But for the volume is now increasing from 2, 1, 2, 3, 4, 8, and 16. So it means that when pressure is reduced by 2, volume will increase by 2. So the factor with which volume increases is also equivalent to the factor with which pressure will decrease. In whichever case, this implies that if you look at the right up there, this particular thing, in this case, 16 times 1 is equal to 8 times 2, which is also equal to 4 times 4, which is also equal to 2 times 8, and eventually 1 times 16. In this first situation, the pressure was 16 and the volume is assumed to be 1. Coming to the second case here, the values changed. The pressure decreased from 16 to 8, then volume correspondingly increased from 1 to 2, keeping the product of the two constant, because 16 times 8 is equal to because 16 times 1 is equal to 8 times 2, which is also equal to 4 times 4, which is also equal to 2 times 8. So in this case, it shows that the law is correct. Now, this implies that, if for example now that this P1 is less than this P2, it means that this V1 will be greater than V2. That's the condition. So in the writing, see what I mean? Anytime P1 becomes greater than P2, automatically V1 must be less than V2, and that is it. So we now go and check the diagrammatic representation again. This is just a way to explain the law. We'll now go to the diagrammatic representation. We go to our file. Yeah, so over here we have a drawing to explain what I've just said. Over here you saw the drawings. Okay, now if you check this particular drawing here, the piston moved up, the piston was released a bit such that the volume around now was, in this case, the volume of the gas was 4, and the pressure here is 1, and the temperature is 300. Temperature remained 300. Okay, let's check a suitable. Okay, yeah, I think this should be better. Okay, now in this case, the piston was moved up, releasing the syringe, which means releasing the force applied equal to decreasing the pressure, decrease in pressure. And when pressure is decreased, the volume was 4, starting from 1, 2, 3, and eventually 4. Then the pressure here, over here, pressure remains 1.0. Then temperature remains 300 here. So now, in this situation, the temperature is constant because it's still 300 in whichever case. In whichever case, I want to see something that will be highlighting this properly well. Okay, here, 300, and that's temperature. But here, pressure is 1.0. Here, pressure is 1.0, but here, pressure increased by 2. So, increasing pressure by 2 automatically implies that volume would decrease by 2 also. Remember here, volume is 4. It might be 4 dm cube, 4 cm cube, but what matters here is the number from 1 to 4. Now, the pressure has been increased by applying more force on the piston, like in the hypodermic syringe. You push it down. Remember that pressure is equal to force over area. Pushing it down have decreased the volume from 4 to 2, so we have 2 now, and that's why the increase is corresponding. So the pressure increased by 2, then the volume decreased by 2, and that is inverse proportion. So it shows that Boyle's law is correct, and remember the temperature must be kept constant. The next thing we look at is the graphical representation of Boyle's law. The graphical representations of Boyle's law. Okay, we have this one here. Whenever you plot P against V, you have a graph in that red. The graph in the red, a graph like this, because at a stage you see that the pressure and the volume will be at equilibrium at a certain point, like here when I used 16, 1, 8, 2, 4, 4. So at this point, that's why this curve. If not, it's supposed to be this way. But because at a stage, there will be where the pressure and volume will be at equilibrium. Now, it also shows what I've told you before, P1 V1 equal to P2 V2, and this shows that when the volume increases, that's the arrow up, the pressure will also do what? Decrease. So let's see other representations. This is another way of representing Boyle's law graphically. So this implies that anytime you plot pressure and volume, like I told you earlier, you have a curve in this way. But if you plot pressure against 1 over volume, that's the inverse of volume, you have a straight line graph passing through the origin, as you can see here, a positive graph passing through the origin. Then, what if you do the reverse? Even if you do the reverse, the same thing will be obtained, in the sense that if we have here volume and here becomes 1 over P, the same graph, this same positive graph will be obtained passing through the origin. So anytime in exam, if they ask you the graph, is it Boyle's law or is it Charles' law? The secret is this: if you watch this drawing, this particular drawing here, it doesn't have anything like temperature. There is no temperature at all. So you have P and you have V, even in this condition, P and V. So if you don't see temperature, it automatically means that it is Boyle's law, because it is only Boyle's law that holds temperature constant, and the parameter that is missing in the graph labeling in the X and Y axis is what is constant. So there is no temperature here, which automatically shows that temperature is constant. So even if you don't understand the lining, if you just see labeling that this is P and the other one is V, you automatically know that it's talking about Boyle's law. But if the graph shows volume and temperature without showing pressure, you know that the graph is talking about Charles' law, probably. So this is the graphical representation. I guess this is a very clear and self-explanatory. Remember to ask your questions using the comment box down there, and other laws will be uploaded here at Her Majesty Easy World Science channel, of course. Now we see other the collection of the graphical representations. Okay. Yeah, so over here we have this graph. Like I told you, here is volume over 1 over P. In the other case we had this is volume over 1 over P, and here the other case we had P over 1 over volume, the same thing. That's here, that's here. Then over here, volume is plotted against pressure. You still have that curve in this form, and these are settled the graphical representation. I guess we are now good to go to the calculations and the cheats involved in this law. Then for these cheats, before we apply these cheats involved in this Boyle's law, okay. Okay, here I'm going to teach us the way to do the calculation cheats. For you to understand the calculation cheat, you still need to understand these particular equations we are saying here. That's P1V1 equal to P2V2, which already implies that, holding on to this, that this particular place is, if you have P1, here is P2, here is V1, here is V2. So let's assume in the question, you see, after setting every condition and you discover that you have that P1 was given, that's the first pressure that was given, was 680 millimeter mercury. Then the first volume that was given was 200 millimeter mercury. Then the second pressure that was given became now 980 millimeter mercury, and you are told to find V2, whereby you make the V2 the subject of the formula from P1 V1 equal to P2 V2. So for you to make V2 the subject of the formula, you divide by both sides by everything surrounding V2 that is not V2, and that is P2, and that is P2. So in this case, you have that V2 will now be equal to P1 V1 all over P2. Now, if you see this type of question in the exam, and lucky enough, you have to see, sometimes in WAEC or even sometimes in JAM, the options are actually saying their answers. They may not even require you to go and press all these things in your calculator, but I will still have questions, real questions that will solve. But I'm teaching you the cheats on what to do. See the law. The law is saying that if pressure is, this pressure here is 680 millimeter mercury, and then it became 980. So there is an increase by 300. So pressure has automatically increased. So moving from P1 to P2 means an increase. And when there is increase in the pressure, it automatically means that the volume will decrease. So moving from here to here will be showing us decrease, meaning that 680 millimeter mercury was increased to 980. Therefore, V2 must be less than 200, because the law says that if pressure increases, volume will decrease. So V2 must be less than 200. And if you look at the option, you become lucky that there is no other option that is less than 200 except one option. That option that is less than 200 automatically becomes the answer. So V2 must be less than 200 in that case. And if you can use your normal reasoning, 680 was increased to 980, almost times they added 300, and 300 is almost getting to half of 680. So which means the answer of this question will be around 100, or it's going to be, it's not going to be, it's going to be more than 100, of course. Yes, it's going to be more than 100, but it will be around 150. Yes. So if we apply what we wrote down here, it's going to be now, let me check if my predictions are correct. My P1 is 680 times my V1 is 200 all over my P2 is 980. So I have to get my calculator here. Okay. Where is the calc? Okay. So I got to divide this so that I can see what I'm up to. We are dividing this. Yeah. So see the calculation here. We punch our calculator here. So we have that 680 divided by, or rather we say times 200 is equal to 136,000, then divided by 980 is 139. So I said it's going to be above 100, okay, within close to 150. So it shows that the volume, the second volume, is 139. So one can confidently fill in the space here, as our final answer is now 139 cm cube. Please, there is a mistake here. Volume is measured in cm cube, not in millimeter mercury. Please, it's measured in cm cube, not in millimeter mercury. Okay, here should be millimeter mercury. Is wrong for volume, please. So here should be cm cube, so that here will also be cm cube. Then remember not to solve when the figures are in different units. So this is the cheat, and that cheat is working. I'll give you another instance before I go and lift questions like that. Another question that you might come across is that after setting everything, you might not know even P1. P1 might be your unknown. Then V1 might be given as 150. Then P2 might be given as let's take it as 2 ATM, and then V2 is given as 300. The units cm cube. Remember to solve in the same unit. Let's assume that this particular V1 was in dm cube and this V2 was in cm cube. You have to convert. Sometimes the exam body will give you such to test you. See what I mean here? If this unit was in dm cube, you can calculate dm cube and cm cube together. It shouldn't be done. You have to convert all either to cm cube or either to dm cube. But let me work with the fact that this one remained in, both of them are all in cm cube. Okay, so now use the reasoning. Normally using your P1 V1 is equal to P2 V2, such that we are looking for P1. Our P1 will be divide both side by V1, divide both side by V1, cancel. We have that the cancel V1 to V1. We have that P1 is now equal to P2 V2 all over V1, such that what we have, the P2 is 2 times the V2 is 300 all over V1, which is 150. So by simple reasoning, like I said earlier, if you check what is happening, because in this case they will either give you two volumes and one pressure, ask you to find the other pressure, or give you two pressure and one volume and ask you to find the other volume. So in this case we had two volumes given, and one pressure given. We are now told to find P1. Compare the ones that were given complete. Volume is complete here, and it moved from 150 to 300. So from 150 to 300 is automatically an increase. So when volume increases, it shows that pressure decreased. When volume increases, it shows that pressure has automatically done what? Decreased. So moving from 150 to 300 is an increase. So where these two started from is going to be automatically 2 times 2 because of the fact that even without solving, because if pressure decreased by 2, which means if you move from 4 to 2, if you move from 4 now to 2, it means that's why 150 was increased to 300. So if you check our calculation here in this aspect, you find out that we are dealing with 600 divided by 150, which is automatically 4. So our answer here is 4 atm. So as far as Boyle's law is concerned, if pressure is decreased to half, so because half of, like we saw in the diagram, half of 4 is 2. If pressure is decreased to half, volume will be increased by 2. So the factor of decrease in pressure is equal to the factor of increase in volume also. So that is it. Now let's see the questions, the real question in this case. Okay. Yeah, over here questions, we will tackle only the ones that is concerned with Boyle's law, and I might also compare the ones that contains Charles' law so that I can distinguish between the two. The general gas equation, that's question 1. Question 1 is asking us about general gas equation. Okay. Now, in this question, the general gas equation is combination of Boyle's law and Charles' law, which is option A. So A is very, very correct. Though I haven't taught you Charles' law, watch my video on Charles' law. I want to separate these gas laws and make all the calculations so easy for you. Then number 2 question say the equation P equal to K over V illustrates Boyle's law. Remember exactly what we did before coming here. You see in the workings, if you come here, we had such thing that K is equal to PV and such that P is equal to K over V, which is exactly what we saw there in the question. So P equal to K over V represents Boyle's law. Then the next question, which of the following relationship, that's number 3, correctly expresses the Boyle's law? This one says this is P varies directly as V, which is incorrect. It is not true for Boyle's law. And temperature is constant. Yes, of course, temperature is constant, but that pressure do not vary directly proportional to volume. Rather, it's inverse. So option A is incorrect. Option B says V varies. They did not give us very well. That's option B is not complete. So then option C says P varies as inverse of V. Very correct. So that is it at constant temperature. This is Boyle's law for you. Then the other one says, number 4 says, the gas law which describes the relationship between volume and temperature is, they said between volume and temperature in this case. Volume and temperature. One should be careful here. We are looking at volume and temperature here. So it is not Boyle's law at all. Boyle's law do not consider that. So Boyle's law doesn't consider temperature and volume. Rather, what Boyle's law considers is volume and pressure at constant temperature. So that's not Boyle's law. Rather, this is Charles' law. Now, what is the value of minus 14 degrees Celsius on Kelvin temperature? This will be discussed in under Charles' law, but it's very simple to do. So what you are just required to do here is your job is just to say minus 14 plus 273. If you are converting from degree to Kelvin temperature, you add 273. If you are converting from Kelvin temperature to degree Celsius, you have to minus 273. Therefore, this will automatically give us 259. There are two correct options there. A and B are all 259, 259. Then number 6 says, which of the following expression correctly represents Charles' law? Okay, I haven't taught you that one, but I'll still answer. That is D. Option D is the correct way because it's a direct proportion between temperature and volume of a gas at constant pressure. Then the initial volume of gas is 300 K and then 200. Okay, this is still Charles' law. But from what I taught you on cheats for Boyle's law, because according to Boyle's law, if volume is according to Boyle's law, if volume is less than V1 is less than V2, automatically P1 will be greater than P2. But in Charles' law, is comparing volume and temperature, and if V1 is greater than V2, automatically T1 will also be greater than T2. That is direct proportion. So looking at this question, the first volume was 220, then the second volume was 250. It means that it increased because 250 is more than 220. So the volume increased. Therefore, the answer must have a temperature above 300. So our answer must be something above 300. So if you are lucky, look at the option A. 183 is below 300. B says 164 below. Then C says 300. It can be. Then D is the only option that is above 300. That is it. This is a cheat. If you know the wordings of the law, you can solve without wasting time. The general gas equation was derived. This question was asked before earlier in number 1. I told you general gas equation is combination of Boyle's law and Charles' law. I'll handle that alongside Charles' law. Then, which of the following statement is true of the molecules of a gas under ideal condition? That is for ideal. And this one will come in when we treat the limitations to this Boyle's law. If the volume of a given, that's number 10, if the volume of a given mass of a gas, this is still Charles' law, is talking about temperature and volume. Then Boyle's law can be expressed mathematically as, they have asked this question and they are asking it again. Mathematically, how do you express Boyle's law? Option A say V varies inversely as P and temperature is constant. Very, very correct. That is the correct answer. Option A. Now, the other question, move over here. The graph above illustrates, like I told you in choosing the graph, just watch here. Here is volume and here is temperature. So what does this tell? We didn't see pressure, and when we don't see pressure is Charles. But when you see volume and pressure without seeing temperature is Boyle's. Simple. Then number 13 says, so the correct answer to this graph represents Charles' law because we did not even see pressure at all. That means what is constant in Charles' law is pressure, and what is constant in Boyle's law is actually temperature. Then number 13 say if 60 cm cube of gas is heated from 273 this to this, what is the new volume of the gas at constant pressure? Constant pressure. They have even mentioned it, telling you to use Charles' law. But if they say constant temperature, you use Boyle's law. Now, the ideal gas equation can be written as ideal gas. We'll handle that one alongside with Charles' law. If you understand Boyle's, Charles' law is a walkover. If the volume of a gas, that's question 15. If the volume of a given mass of gas at still temperature and volume, that's Charles' law. To what temperature must a gas be, that's number 16. To what temperature must a gas be raised from 273 in order to double both its volume and pressure? That's general gas equation. It will come later with Charles' law. And if the temperature T of an ideal gas is increased. Okay, still for ideal gas, that's ideal gas equation. Then number 19, I think it concerns us. In Boyle's law, option A says T is constant, yes. Why P varies directly? No. P doesn't vary directly. P varies inversely. There is inverse variation. This directly is what made the option A wrong. Then option B says pressure is constant. Pressure is never constant in Boyle's law. Rather, it is temperature that is constant. Then option C says V is constant. No. Volume is only constant for what we call pressure law. Pressure law, or the so-called Gay-Lussac's law. But don't see Gay-Lussac's law of combining volume here. No. That's not what I mean. Pressure law can also be called Gay-Lussac's law. That reminds me, I'm going to establish a kind of little difference between these three. There are conditions where one is constant and the other. Fine. So here I want us to see a little bit clear difference. What is constant? Boyle's law. In Boyle's law, the constant there is temperature is constant. So we say that temperature is constant in Boyle's law. Then in Charles' law, pressure is constant. Then in pressure law, volume is constant. So in a situation whereby all these three varies, you call it general gas equation. Now in Boyle's law, if temperature is constant, it means that Boyle's law is relating two things, is only showing the variation between volume and P. That's for Boyle's law. Then Charles' law is only relating the relationship between volume and temperature, since pressure is constant. Then pressure law is relating what happens between temperature and pressure at constant. So here the K is automatically T. Here the K is automatically P. That's for Charles' law. And here K is volume. That's for the so-called gas law, or the Gay-Lussac's law, but not Gay-Lussac's law of combining volume. And that reminds me, another name for this Boyle's law is Mariotte's law. You can call it Mariotte's law. So Boyle's law can also be referred to as Mariotte's law. Okay, you either call it Boyle's law, or you can also call it Mariotte's law, because around I think in 1662, if I'm correct, Boyle discovered this law, and around 1670, I guess 1676 or so, this young man Mariotte in Europe independently discovered the same law. So people might call it Boyle's Mariotte law. So don't be confused when you see Mariotte's law. It's still the same thing as Boyle's law. So the next thing we see is the limitations to this Boyle's law. According to our study plan, we will see the limitations. But before we go to the limitations, let's answer this last question. Eventually, I'm in question 19. It's saying the correct way. Then option D says T is constant, while V varies inversely with P. Very correct. So option D is correct in question 19. Then 20 says the initial volume and pressure of a given mass of a gas is V and 3P. Then I say, what is its pressure if the volume is increased to 2V at constant temperature? This is exactly the Boyle's law we are talking about. So we will use this note here. Okay. Let's clean off. We'll be solving question 20 over there. And the question told us, let's see it a bit here. We are going to use P1 V1 equal to P2 V2. Simple. These particular figures, just assume that this V is 1V and then this 3P is 3, just 1. So you can even predict the answer without solving, because if pressure here, if volume here is 1, that's if volume in this condition is 1 and the pressure here is 3, then eventually making the volume 2 means that volume has increased by 2, which means pressure will decrease automatically by half, which means you say half of 3 times that 2, which will give you actually it's going to give us 3 over 2 in the whole scenario. So but let's solve and see. It's going to be option C, that's 3 over 2p. But in the solving, coming over here, our P1 is 3p, our V1 is V, then our P2 is unknown, our V, I guess, yes, our V2 is 2V. So what do? You just make the P2 subject to the formula, and P2 is equal to P1 V1 all over V2, and P1 is automatically 3P times V1 is V, and then V2 is 2V. So you see, V will cancel V, so that we are left with only about 3P over 2, which is the same thing as 3 over 2P, which is option C. Option C, either, don't mind my circling there, and that's option C. Okay. So option C should be the correct answer. Okay, then the limitation to this Boyle's law is simple. The same limitation to Charles' law is also the limitation to Boyle's law. What is an ideal gas? This law is only applicable to an ideal gas. Yes, and an ideal gas do not exist. It's a perfect gas, a gas on assumption. Any gas that obeys Boyle's law and Charles' law at all conditions of temperature and pressure is seen as an ideal gas. So the little limitation we might have is, the little limitation to this particular law is that we are considering the limitation. So we have the limitations of Boyle's law limitations. So we now still go back to our normal writing. One is that it is only applicable at all conditions of temperature and pressure for ideal gases. But for real gases, for this to apply, it is only correct when the temperature is high and the pressure is a bit at high temperatures and low pressure. This law is obeyed correctly, but at low temperature and high pressure. So the limitation is that there is a remarkable deviation. There is a remarkable deviations at high pressures and low temperature. So this law is only perfect when the temperature is high and the pressure is low, such that it's going to assume to be in continuous motion. But you compress this gas. If you compress this gas at a very high pressure and low temperature, this Boyle's law shows a lot of deviation. So the limitation is that the deviation is very much at the conditions of high pressures and low temperature. Remember, we are still on with Her Majesty Easy World Science channel, the Easy World of Science. You're going nowhere better than this channel. So please, I'm encouraging you that is watching to please subscribe. And also share this video. Share, for I cannot do without you. So there is love in sharing, and especially what if you are sharing the good stuffs. Remain majestic. You have to remain majestic, of course. Bye for now.